All right. Yeah. Hello, everyone. My name is Nam. So today I am giving you a lecture. So you have learned from previous lecture about how to generate a language with the language model, how to generate an image or video with some generative model. So today we will learn about how to generate the other things. Maybe you can guess either the speed or audio or maybe the song. So the topic today is a neuron text-to-speech synthesis. So in this lecture, you will apply some knowledge you learned from previous lecture, like sequence-to-sequence model or generative model. So I would consider this lecture as a research lecture, not too much theory or too much mathematics. So the outline of the lecture today is first I will introduce some background about the text-to-speech. And next I will introduce about some most recent model of text-to-speech or some state of the art. Some state of the art model in text-to-speech domain. And next I will talk about some advanced topic in text-to-speech synthesis. So basically, speech synthesis is one of many topics in speech signal processing. Yeah, we have a speech recognition, speech synthesis, speech enhancement, speaker recognition, speaker diarization, for example. And in speech synthesis, we have two kind of a main problem, like text-to-speech synthesis, what we are talking today, and the voice conversion. Text-to-speech is something like we synthesize the speech from text, and voice conversion, I mean, we change the voice from the other voice, or maybe we change the prosody or change the accent or different aspect of the voice. And there are different kind of topic like speech synthesis based on brain signal or speech translation. That means you translate the speech from another language. So today we will focus on text-to-speech synthesis. So, okay. So what is text-to-speech? Text-to-speech is a system can generate the intelligible and natural speech from text. So basically, we have a text, and the text-to-speech system can generate the audio with this content. So it's a very important part of the AI system because it's like we train the machine to know how to speak. From ASR, that means we train the machine to know how to listening. And yeah, so next week we move to the pipeline of the text-to-speech system. So how we come from the text to the waveform audio. Yeah. So there's many framework can help, can move, can come, can generate the audio from the text we consider here is a character. So first framework is work like, first we come from a character to the linguistic feature. What is the linguistic feature? Linguistic feature just mean the linguistic feature of the text. So for example, we need to provide the model a lot of information of the text, not only the character, like how the word segmentation, how the post stacking of every word, like this word is a noun or adjective or adverb or prosody. Like this word need to be stressed or not. Grapheme to phoneme. That means from this character, from this text, we need we need which sequence phoneme is corresponding to this text. So this means a linguistic feature. Yeah, from the it's like a traditional pipeline of the text to speech. I mean, it's from the past, a long time ago. So from the linguistic feature, we build the model, the acoustic model, to generate the acoustic feature from the linguistic feature. So for a long time ago, the acoustic feature is some feature from signal processing like MFCC, base frequency, BAP, or BFCC. So we need a lot of knowledge from signal processing to do this, and because mostly they use mostly the Fourier transform to generate this feature. So we can think about to do the inverse Fourier to generate the waveform from this feature. But actually, it's not quite easy like this, because when we do this feature, we use the power spectrum, so it's lost the information of the phase. I mean, we only have the information of the amplitude, so it's quite hard to do the inverse Fourier to transform this feature to the waveform. So in the past, so they have developed some signal processing algorithm to convert acoustic feature to the waveform. Like it's called stress word or LPCnet. So yeah, so it's what the research did in the past to generate the speed from the text. Next, something more fancy, more easy to do is we just need the information of the phoneme, and we have some acoustic model to convert the phoneme to the acoustic feature. And then we also use some statistic, some signal processing algorithm like straightforward to convert the acoustic feature to the waveform. This kind of the algorithm straightforward, we call it a vocoder. That means we convert the acoustic feature to the waveform. We call it a vocoder. But it's a traditional vocoder. That means it's a signal processing vocoder. So recently we don't use this anymore because we have some more fancy vocoder, because we have a lot of of the deep learning and neural network model. Yeah. So so there are different pipeline. We come from not phoneme, we come from phoneme to the MEL spectrogram, which are more easier to compute than the other acoustic feature. And the MEL spectrogram, we use the green film lymph vocoder to generate the waveform. Green film lymph vocoder, something like, it's also the signal processing vocoder. It's not related to neural network, and or we can use the vocoder here, wave globe. You can see here, flow wave nets, melgan, hi-fi GAN, diffusion wave or wave breath to do the vocoder, to build the vocoder. So today we will focus on this kind of pipeline. So we have the acoustic feature model, which can generate the MEL spectrogram from the phoneme, and we have the vocoder. One moment. Right. Right. Sorry for the interrupting. So we will continue right now. All right. So yeah. So today we mostly focus on this pipeline. I mean, we build the neural network model to generate the Mel spectrogram from the phoneme, and we build the vocoder to the to convert the waveform from the Mel spectrogram. Yeah. So the we have a three component in the text-to-speech system. First is a text analysis. I mean, we convert text to a linguistic feature. Secondly is acoustic model. We convert the linguistic feature to acoustic feature. And finally is a vocoder. We convert the acoustic feature to the waveform or audio or speech. So text analysis is mean we do something like text processing. I mean we do the document structure detection. I mean we separate the document to many sentences. We do the text normalization. I mean we remove the punctuation, or we do the uppercase or lowercase. Linguistic analysis. I mean we do something like post-tagging. Like we need to know this word is a noun or verb or adverb, or polyphone disambiguation. This means, yeah, polyphone disambiguation. That means we have the word can be pronounced in two or more different ways. So it depends on the word sense. So we need to know how to pronounce the word in every case. And the grapheme to phoneme convergence. I mean, we transform is the most important part in the most recent TTS, because we need to transform the character to the phoneme, the sequence of character to sequence of phoneme. So we can, based on dictionary, or maybe we can build some neural network model can transform the character to the phoneme. So yeah. So next we talk about the acoustic model. Yeah, the lie in speech recognition. In the past, we based on statistical parameter speech synthesis.
Yeah. So first, I will move to the ion-based acoustic model. So yeah. So we can consider the TTS as a sequence problem. That means we generate another sequence given the input sequence. So we can think about using some sequence to sequence model, like in speaker like in speaker recognition or machine translation. Yeah. So the motivation of the tacotron is come from sequence to sequence. That means we need the encoder and decoder, and also the attention mechanism to generate the Mel spectrogram from the phoneme. So yeah, basically it has the two parts. It's an encoder and decoder. Encoder is transform the text to the text representation, and the decoder when decode a Mel spectrogram step by step by given the output from the encoder. And of course, it needs the attention mechanism to to learn how to align the text with the audio. Yeah, and in the tacotron one, we based on LSTM, and even tacotron 2 is also based on LSTM. But the different thing between the two versions of tacotron is in the first tacotron we use a green film as a vocoder, and in second tacotron we use a wavenet as a vocoder. That means we use a neuron vocoder. So it make the natural improve the naturalness of the audio. And you know about the in the transformer, we talk about the multi-head attention, but here in the very first model, very first sequence to sequence TTS model, we use the location sensitive attention. That means we need the attention information from the previous step as the input of the attentions. Yeah, and we can train the control like the sequence to sequence by using the teacher forcing. I mean, we know the input of every step and we know the output in every step. So the different thing between the speech recognition and speech synthesis, that means in the speech recognition, we have a stop token and start token to decode, right? So in speech recognition, we decode until we last token. And so, but in the tacotron, we have spectrum. So how do we know when we need to stop? So beside decode the spectrogram in every step, we try to decode the something like stop token. That means it's a binary classification. In every step, we can know it should be stop or not. So it that has two value, 0 or 1. So when a stop token has the value 1, so we don't need to decode anymore, and the model will stop in this at this step. Yep. We also have the CNN-based acoustic model. We call deep voice tree. It's also the sequence to sequence TTS. I mean, it have the encoder and decoder, and also the attention mechanism. But mostly it's based on CNNs, not LSTM. And there's a it try to do the multi-speaker, support multi-speaker. What is a multi-speaker here? This means we have the one TTS, but we can train with the data spoken by a lot of speakers. We can to record and the data is one speaker. So yeah, that's the different things between the deep voice and tacotron. And also yeah, some minor modification like they use three vocoder, green film, and word and wavenet to train at the same time. Yeah. So next is a transformer-based acoustic model. Yeah, you can see the diagram is quite similar to the speech recognition diagram, the transformer-based speech recognition model, right? So we have the encoder which transform text to text embedding, and we also have the positional encoding to have the model have the attention know both position of every step, and the model will produce the mail spectrogram and also the stop token like in tacotron model. The good thing of the transformer is we can train parallel, right? We don't need to train step by step like LSTM. So each train is more stable and faster to converge. But the attention will be more challenging than the tacotron because the tacotron only needs one attention between the encoder and decoder. But the transformer-based model, we need a lot of attention in there because every layer has a attention mechanism, attention, the multi-head attention. So yeah, so the performance is not improved if we compare with the tacotron, but it can help training more easier. Yeah. So yeah, so maybe the sequence to sequence is something non-autoaggressive, so it can be too slow. It's not fancy like autoaggressive. So we maybe we think about make the model more faster. So autoaggressive and yeah. So we move to the fast speed with a non-autoaggressive model. Sorry, the tacotron is autoaggressive and it's not enough fast as autoaggressive. So that is the motivation of the fast speed. I mean, we try build the non-autoaggressive TTS. So that means we need to generate the mail spectrogram from the text directly without attention, without and two-part encoder and decoder. So yeah, it's quite, you can think that's how we can do this because the mail spectrogram is very long, right? It's the length of the audio, and the length of the text is much shorter than the length of the audio. So how we can map between the text and the audio without the sequence to sequence. So in the fast speed, we try to do some. We firstly the phoneme embedding will come to the transformer encoder to generate some phoneme representation, and to mask the length, to make the length of the phoneme and the length of the audio are equal. They use some upsampling technique. That means we upsampling the phoneme to master the length of the sequence of audio. So how to but we need to know how to upsampling, right? How to upsample. They use some external model called the duration predictor. That means we predict the duration of every phoneme by some kind of by some external model. So we can know the duration of every phoneme, and we can base on this information upsample the phoneme representation to mask the length of the audio, mask the length of the mail spectrogram. And in the first fast speed, this model is trained. Two model is trained separately. I mean, we train we need to train duration predictor first by using some. Okay, so how to train the duration predictor? Because we need the duration of information of every phoneme to train, right? So to know the duration of every phoneme, we can use every alignment model like speech recognition. If we use, we have based on this alignment, we can know the duration of every phoneme from from which time, which point to which point. Or maybe we can use the text to speech, because the text to speech also have the alignment, so we can know the element of the every phone like in the speech recognition. So when we have a duration of every phoneme, we train the model to learn how to predict this duration, and we apply it on the fast speed to know how to upsample the phoneme representation to mask length of the Mel spectrogram. So finally, we don't need attention mechanism, and we can generate speed non-autoaggressively. Okay, so we will move to the second fast speed. So what is different in the second fast speed? In the second fast speed, they don't need a second external duration predictor, because they train durational predictor, and is they integrate the durational predictor in the model. So we have the new component called the variance adapter. That means this variance adapter predict the duration of every phoneme, the pitch of every phoneme, and the energy of every phoneme. So that's why we need a lot of but to train this, we need the external model to know. External, it's not a model, it's some kind of processing to know, to predict, to know the energy, the frequency, and the duration of the every phoneme. So the model is trained end to end, but we need a lot of pre-processing steps. So yeah, so to make the pipeline more easier to train, so they need a lot of pre-processing step. But finally, the model can be trained end to end without the external duration predictor, because everything is the duration predictor, energy predictor, any predictor is included in the variance adapter. So the good thing of the fast pitch tool, that because we have the variance, if we change the energy information, we move the frequency of the output of the speed also can be modified. Yeah. You mean after the variance adapter, we have the positional encoding? I think basically you're right. Maybe we don't really need this, because mention a position for the first step, right? Yeah. And in every step variance adapter, we also add more residual connector to keep the information from the first step. I think we have a length regulator step, I mean the upsample step. If we add more, the information would be helpful. We upsample the length, it can be modified. Then one more time we add the information to the representation. I think it could be better. Okay, so yeah, so the good thing of the fast speech tool, I mean we train end to end, and we can modify the speed in the various adapter. So next we move to the vocoder. It means we convert the MEL spectrogram to the waveform or to the audio. So the very first vocoder we call it is called WaveNet. That means the auto-receive model with a dialect causal convolution. So yeah, so like its name, it's based on convolution, and it's auto-receive. So basically, from it predict the waveform, right? It generates the waveform, and in every step, is predict the next waveform. It can train the forcing. Yes, like auto-receive, we input the current step to predict the next step. So here, the waveform mostly is based on 16-bit value, right? So it's had around more than 60,000 value. It's much for the neural network model. So it can cause up dimensionality. So the idea here, that means we reduce the number of the value to be predict by using some quantization technique. So we can reduce more than 60,000 values to 156 value. And of course, we can convert back from 256 to the original values. So in the WaveNet, they use a dialect, the causal convolution, because it has a bigger receptive field than the normal convolution. So here in every step we have the information of the 16 previous step. So the receptive field is bigger if we use the normal convolution. It's bigger than we use the thing here. We need to convert the MEL spectrogram to the waveform, right? But we don't hear any MEL spectrogram as an input in this diagram, because the MEL spectrogram will be the input in every step. That means the output of every step will conditioned not only by the previous step but also conditioned by the MEL spectrogram. Yeah, I think it's easy to know which MEL spectrogram corresponding to which step in the waveform, right? Because it had because the MEL spectrogram is computed from the waveform, so it's easier to know which MEL spectrogram need to input to which step. And this WaveNet can be trained to do the TTS only. I mean, it's not the vocoder. It can be trained as a TTS model because it can condition by the text. But if we do the TTS, the situation is more difficult. It's more challenging because to which step in. So we need to do some alignment gains. It's more than if we confirm MEL spectrogram. So yeah, so we have learned a lot of generative model from previous lecture, like GAN, variational autoencoder, or normalizing flow or diffusion model. So of course, we can use this kind of model to generate the waveform from the mail spectrograph. One thing I forgot to mention about the vocoder, that's we yeah, we can think about the L2. I mean, the loss, the mean square error between the target and predict to train generate the waveform, but it's not suitable for the vocoder, because in the vocoder, if we use the L2, so we just shift the audio 1 millisecond, so the loss will be much higher. But the out, right? So it's not suitable if we use the L2 loss for the vocoder. So basically, we use some different loss, like here in the WaveNet, we use a cross entropy because it's a classified problem. We classify to 256 value, so we don't use the L2 loss here. And also in the different things, if we use a generative model for the vocoder, we don't use a L2 loss in the waveform. We can use the loss of the generative model like the KL diversion, and yeah. So we will move to the generative model. What we need to use to do the vocoder, to train the vocoder. Maybe you have learned from previous lecture about the flow-based generative model. It's the flow to try to solve the density estimation to model the probability distribution of the data have been seen. So they use a normalizing flow to do this. And in this case, the loss function is minimize the negative log likelihood of the observed data, and which can be attributable by the variable formula. So basically, we have some noise Gaussian, and we have some normalizing flow. We can translate, we can convert the noise Gaussian to the real data. And also, with the normalizing flow, we can inverse the real data to the noise loss distribution. So by this way, we can easily to compute the log likelihood of the negative log likelihood of the observed data by compute the log likelihood of the noise of the generated of the noise, because we have the inverse way, right? We can generate the noise from the observed data. If we have a noise, we can call the probability distribution of the noise, and from this we can compute the probability distribution of the observed data. So we just yeah. So how we apply this kind of model to train a vocoder, to make a vocoder. Yeah. So we have some model we call the parallel WaveNet. I mean, we have a two WaveNet here. It first is a WaveNet picture. That means it comes from the normal WaveNet, and we have the WaveNet student that we come from the noise, and we use some normalizing technique to generate the waveform, and we use the WaveNet picture to train the WaveNet student. Yeah. And also we have the wave flow, which also come from the noise, and come from the noise. We can compute the probability distribution of the waveform by using the normalizing flow. And the purpose so the loss is wouldn't be the optimize the minimize the negative log likelihood of the observed data. Yeah, it's quite interesting if we can apply the normalizing flow to do some vocoder. And the normalizing flow not only apply on the vocoder but it can be also applied on the acoustic model. Like in the glow TTS, they come from the text. They use some encoder to predict the prior of every phoneme in the text. So every phoneme has the mean and variance. So and the decoder is based on the normalizing flow. So basically, we can compute the latent from the Mel spectrogram by using the inverse decoder. So with this kind of latent, we can compute the distribution of the latent because we have the prior from the latent and compute the probability distribution of the latent. And with the probability distribution of the latent, we can also use the rising flow, the chain variable formula to compute distribution of the waveform of the Mel spectrogram. So finally, we have the probability distribution of Mel spectrogram given the text. So that's the idea of the glow TTS. So this model is also the non-autocracy because it also have a duration predictor. But how to train the duration predictor here? So we have a latent latent distribution because we can do the inverse diagram. So after we have a latent right of every phoneme, we learn the alignment between the latent and prior of the every phoneme. So basically, we can know the duration of every phoneme. So after we have duration and alignment of every phoneme, we can train the duration predictor to predict the duration of the every phoneme. So that's the idea of the glow TTS. So we don't need the external alignment anymore because we can, based on the latent and the prior distribution of every phoneme, to build the monotonic alignment. And based on this information, we can predict. And we can train some one kind of generative model to do the vocoder like GAN. So GAN, we have a two-step, the adversarial step. In the adversarial step, we need to train the generative component generator to cheat the discriminator. That means it will try to produce very realistic data. And in the discriminator step, we will try to train discriminator to classify the data from the data generated from the generator is a real effect. So that's the two steps of the generative model. So yeah, to build the generative, to build again for the vocoder is quite simple because we can, based on the transpose convolution, we can upsample the Mel spectrogram to have a same length as the waveform. So from the MEL spectrogram, we use convolution and upsampling layer to generate the raw waveform. And discriminator will classify this raw waveform is a real of by using not only the output but also use the output of the every feature map, because we use the CNN, right? So we have a lot of level, a lot of feature map level. So it's not discriminate the layer, but so discriminate in where every feature map layer. Yeah. So yeah, the framework is quite easy, right? Thing here is we need to think about the architecture of the model, how to design the convolution efficiency to generate the waveform from the MEL spectrogram. And after we have a good architecture, we can apply the training mechanism in the game, the vocoder. And the hi-fi gun is also and it's also generates the MEL spectrogram to the waveform. And it's not use two kind of discriminator. The first is a multi-scale discriminator. This means we discriminate the feature from every layer of feature map. And multi-period discriminator, that means we discriminate the feature from not only in every layer feature map, but also the small part of the feature map. Like here, we apply the discriminator on the one dimension of the feature map, or the horizontal dimension you can see here. Okay, so next we move to the fully end-to-end take-to-speed. So what is a fully end-to-end take-to-speed? That means we come from text or phoneme to the waveform directly. That means we don't the acoustic model or vocoder. We combine two components to one together. Yes, so it has a many advantages. First is a fully differential optimization. I mean, we only train one model for all. And it's reduce the cascade error. That means if we have for example, if we have a acoustic model and a vocoder, so we can cumulate the loss of the error of the both acoustic model and the vocoder, and no MEL spectrogram bias, because the MEL spectrogram is not the only the optimal goal. So yeah, so we come from first the very first the fully end-to-end take-to-speed. So the it's called the fast speed 2s. That's based on the fast speed second, fast speed 2. And the idea is very simple, because we have the but it has a length as a MEL spectrogram, right? So the idea here is we add the waveform decoder on the top of the phoneme representation to produce a waveform. So finally, when training, we have a code to decode the MEL spectrogram, and second, we have the waveform decoder with form. And the waveform decoder can be similar to any vocoder like WaveNet, WaveGlow, or hi-fi gun, for example. And yeah, we use same loss and same loss function as this kind of vocoder. So basically, it's kind of the end-to-end, but it's not really end-to-end because we still need to train the male spectrogram decoder and waveform decoder at the same time. So it's like the waveform decoder is just training the waveform decoder is just like auxiliary task for fast speed. So we've moved to the thing is more fancy. In VS, VITMS is something like very different speed synthesis. So this model is kind of with the augment by the normalizing flow and generative model. So the here you know the very stereo encoder. Second is the decoder, the prior. And here we to input the pricing autoencoder is a linear spectrogram, and the output is a raw waveform. You can see it in the left side of diagram. It's a variational autoencoder. So yeah, so the variational autoencoder encode the spectrogram to the latent variable, and the decoder convert the latent to the waveform. And of course, because the decoder is generate the waveform from the latent, so the decoder can be designed like the vocoder. We can use a high frequency, wavenet, or the post stereo encoder. So when the training variation autoencoder, we need to minimize the KL diversion between the post stereo encoder and the prior, right? And the prior learned in previous lecture, I guess it's similar to the Gaussian distribution, right? But here, the prior it's not similar to the Gaussian distribution. I mean, zero mean and unit variance, because the prior conditioned by the text, so is a condition of prior. That means the prior here is depend on the phoneme input. So how we compute the prior? This prior we compute by using the normalizing flow, like in the glow TTS. I mean, we have the phoneme input. We project the phoneme input to latent distribution. We have a mean, and you can see on the right side of the diagram, we have mean and a variance of every phoneme. And we can here we have the one normalizing flow component. That means we can inverse the latent from the posterior encoder output to have the latent variable here. And we can do we can compute the monotonic, we can do the monotonic alignment between the latent variable and distribution of every phoneme. Because if we can compute the distribution of the, you can use a chain variable formula to compute the prior by using a normalizing flow. So after we have a normalizing flow, we can use a KL diversion to optimize the posterior encoder. And also we have the loss from the decoder, because the decoder is based on the vocoders. Like in the VITS, we use a high frequency for the vocoder, so we can compute the loss for the decoder by the high frequency. We can change the posterior encoder by optimizing the KL diversion between the conditional prior and the posterior encoder. And also we have a lot of auxiliary, like because we have a waveform, so we can use a Fourier transformation to where to compute the spectrogram of the output. So we can use a L2 loss to optimize the model by the loss between spectrogram of the output and spectrogram of the input. Yeah. So it's the loss of the variational autoencoder loss. So it has the KL diversion loss. That means we minimize the KL diversion between the posterior encoder and the prior conditional prior. We have a duration loss. I mean we compute loss for duration predictor. We have a reconstruction loss. I mean the loss of the decoder or the loss of the hi-fi GAN. Of course, we have because it has a GAN, so it has the adversarial loss. So next we move to the advanced topic in the text-to-speech. So we have a different kind of topic in the text-to-speech. So the expressive controllable TTS. That means we not only produce the voice, but we can control the different aspect of the voice, like the accent, the emotion, or which word we need more. Or robust TTS. I mean we need TTS sound more natural, sound more like human speech. Model efficiency in TTS. I mean we need the TTS model can be more and more faster. And that's efficiency in TTS, like multi-speaker TTS. I mean TTS can generate multiple voice, and multi-language TTS. I mean TTS can use the audio for many languages. So so we can see some similar between the TTS and speech recognition. Some similar topic between speech recognition. We also have some topic like multilingual speech recognition, speaker for speech recognition, speaking with emotions recognition. Yes, it's quite similar, but here we not recognize. We try to synthesize. So expressive net TTS. What is a expressive TTS? So when we could consolidate the emotion environment where where to say, and we smooth the prediction by the output is not only one, but can be a one-to-many mapping. I mean, with one test we can produce more, can produce more output, because like human we never speak one sentence in the same way. So yeah, we energy of every word or every guy can be considered like expressive TTS, or we can have some deep voice. We can do the multi-speaker TTS, so it can be considered as the multi-speaker TTS. Yes, so there are a lot of things we can control in the TTS model, or even prosody. To control prosody is very simple. That we have something like prosody embedding. We can generate from with the speaker embedding in the encoder, and so we add the information of prosody to the encoder, and decoder can use this information to decode the audio this prosody. And we can control the style of the TTS by use style to have a dictionary, and we can compute the attention between the reference audio and embedding to figure out which the style corresponding to this audio. With this, with embedding, we can concat to the encoder output, and the decoder can generate the audio with this style. Yeah. So other kind of the familiar problem of TSS is have the word skipping, repeating because it's attention. And if the attention collapse, we can make forgot a word, or maybe it can repeat this a word. So it's one. So how to eliminate this kind of error is one kind of task in robust TTS. So the solution is a enhanced attention mechanism. We try to do attention better, or we can replace attention with duration prediction in fast speed or glow TTS or VITS. We can replace autoaggressive by non-autoaggressive, like in also fast speed or non for or glow TTS or VITS. We use a non-aggressive, so we don't need attention. So it can make the TTS, we can robust TTS to eliminate the kind of a lot of error like word skipping, repeating. Yeah. So how to improve the attention? Well, because the in the TTS attention is the monotonic. That means it follow like in the see in the left diagram. That means it moves like linear. It doesn't. For example, in the machine translation, it's not a monotonic alignment because every word it needs to attend in the software sentence in different order. In the listen or text to speech, the alignment is the monotonic alignment. So we have some technique to force the attention to produce attention component to produce some monotonic alignment. Yeah. Yeah. So like in the tacotron, they use some location sensitive attention. So they use attention from the previous step to input to the next attention. So it's something like tells you need to that I have this part, so please don't attend on this part anymore. That's so that's why on the tacotron they use a location sensitive attention. So and the transformer doesn't have the location information in the multi-head attention. So the performance of the transformer TTS is not much better than the tacotron. Yeah, so it's that similar. Yeah, in a speaker recognition, the transformer is maybe better than LSTM, but here it's not. it's not much better. Yep. So we can foster attention monotonic like in this image. Yeah. So in the left diagram, it's a soft attention. I mean, it's attends the model attend everywhere in the short input, but we try to attend more orderly, right? It's called the monotonic attention. Or we can do the multi-frame prediction. I mean, in every step, we not only predict one Mel spectrogram, but we can predict a few Mel spectrogram steps. So if we use a multi-frame prediction, so one step had a lot of information of the audio, so it can help the model do the attention better, and it helps the model train much faster and also and more stable, and it increases the conversion speed. Yeah, also we can add dropout in we got the prenet to model avoid the attention is overfitting to the train data. So model efficiency, I mean, we can train the TTS with a much smaller, much faster by using some technique like pruning. This means we remove the weight we don't use by using quantization, knowledge distribution, like we use a big model to 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 train the smaller model by using some loss like KL diversion and use run architectures, and also with efficient modeling with a domain knowledge, like we use a linear prediction, multi-band modeling, subscale prediction, multi-frame prediction, and streaming synthesis. Then you can see here the 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 complexity of the is the ON, but for non-autocracy model like fast speed or flow VIS, the complexity of the model is the O1, which is much faster and efficiency. And of course, we can use one TTS model can generate audio for every language. So we call the multilingual TTS, right? Like the multilingual speech condition we have here, we have multilingual TTS. And also we have the so we can apply some technique. We can apply on speech recognition for, we can apply it on multilingual TTS. And also we can have a speaker level TTS, I mean TTS for everyone. This means we have a TTS which can be trained on multi-speaker, and we can adapt this TTS on your voice even your voice has not been seen on a training data. Or we call it a zero source TTS, zero source speaker TTS. I mean we can produce the voice which has not been seen in the training. Yeah, it's called as voice adaptation, voice cloning, or custom voice. Yeah. So how we can adapt the model to produce the new voice, but we need to fine tune it very fast and doesn't require much data. So some author proposed the ADA-speed. ADA that means the adaptation. So it's based on the fast speed, but it has some conditional layer normalization. because fast speed is based on transformer. So it has a layer normalization in every layer. So if we can change the scale layer normalization, so we can change the voice of the output. So in this model, the layer normalization is also receive the input from the speaker to scale the model to produce a different voice. So when we have a data of a new voice, we only fine-tune the layer normalization on this voice without reach the model, without reaching every parameter. We only fine-tune layer normalization on the new voice. That is how the model train to adapt the model to generate a new voice without train too much a parameter. And if we want to adapt model on to generate a new voice without, if we have the data without transcript, so how we can do this? And in the adapt speed second, they they have they propose a framework can help us to train to adapt the model without a transcript. First, we have a original TTS model training with a no speaker, with a lot of speaker. And with a new speaker, we have audio, right? And we can generate a mail. And we train the mail encoder to generate the representation from the mail spectrogram of the new speaker. And we use a decoder we had already trained to generate the audio. So by this way, in the second step, we try to train mouse encoder to generate the representation, which is similar to the phoneme representation, which is already training. Because the mail decoder is free, it's will be it doesn't train, it's not be trained in this step, but it still can produce the audio because the mail encoder is encode the audio to similar representation as the phoneme encoder. At the next step, we fine-tune the mail decoder to produce a new voice. And after all, we can so we can have the model, we can produce audio with a new voice, even the new voice doesn't have the data with the transcript. Okay, so it's summarize. It's my summarization about the some kind of the TTS model, some neuron TTS model, and some advanced topic in the TTS domain. And thanks you for your attention. The role of because the duration predictor is used for the non-autoaggressive TTS, right? So so for the non-autoaggressive TTS, it doesn't need the attention. It just need to how to upsampling from the phoneme representation. So that's why if we have the phoneme duration predictor, we can know how to upsample from the phoneme. So when the model has the phoneme representation, has the equal length, has the spectrogram length, so it doesn't need to attention anymore. So if you use attention, maybe the attention can forward some word, right? But if we do everything non-autoaggressive, it's come from word to the mass spectrogram directly, so it doesn't, so it cannot be forgot anything. The word cannot be forgot. Okay. I hope I explained clearly. Okay, so yeah, any question? Okay, so if you don't have any question, I can end lecture here. So thank you very much. Yeah.